All right, here we go. Finish up 6.6. Going to take do 6.7 as well in the same screencastify, so we can basically get done with both of those today, Thursday, obviously. Hopefully you have headphones, so not everybody hears my voice echoing around the room. All right, so here we go. So we're sitting on, what page are we on? Page 25, I think? Yep, I'm on the wrong page. Yeah, bottom of page 25 underneath, or kind of middle of page 25 underneath that picture. So here we go. Fuel rods, fifth period. I know you're going to repeat yourself just a little bit, but here we go. Fuel rods are the tubes that contain the uranium pellets. Then you also have the control rods. These are the guys that are highly, highly, highly important, because if those guys weren't around, that chain reaction of nuclear fission just goes crazy. So the control rods are the ones that absorb the excess neutrons, so that way that chain reaction stays controlled. So that way it prevents the meltdowns, prevents the fires, explosions, stuff like that. Now, what a meltdown is, this containment chamber is basically a couple layers, a couple cement layers that are all like a foot or two thick. So basically, if a meltdown starts to occur, hopefully it has to get through all the concrete before it really starts to hurt anybody. All right. I'll get myself out of the way there. So basically talking about there, fuel rods become too hot and melts the water boils away, and the radioactivity gets released. All right. Now, uranium mining, okay, has all the same drawbacks of regular mining, mountaintop removal and strip mining and subsurface mining, all that kind of stuff. All the bad things there that are from the regular mining for coal and stuff like that, still the same. But the big difference, you simply don't need as much uranium. So instead of just this ginormous open pit mine like in Utah, it's still an open pit mine, but it's just a much smaller version is basically the idea, because you need less of it for the electricity. All right. So hopefully you grabbed a colored pencil up front. Flip back to number 12. The red, green, and yellow, they're all the same. Basically, just mark on your map whatever color you have, put your little legend, nuclear energy, mark down some of the big ones. Obviously, you can see that Canada, big green dot, has the most. All of it uranium output in 2005, shown as a percentage of the top producer. So Canada's the top. Then it goes to the yellow. So you can see over in Kazakhstan, you can see in Australia has a ton of it. South Africa has some of it. Namibia is there as well. Then the red, you can see kind of the northeastern of the United States. You can see over in Europe, parts of China, parts of India. But basically just mark the spots down on your map as nuclear energy is all it is. Okay. So the on the top of 26, it says locations of uranium mines. That's just there. You don't need to write down those names of those, but that's okay. So just kind of skip that part. That one spot, it says Wyoming uranium mine pollutes drinking water by contaminating the. What this does, threatens the drinking water. So you can see class 3 mining versus class 1 disposal. So basically with them mining uranium, they're pulling up a bunch of water there. That water is being contaminated because of that. So basically that blank there, they are contaminating the shallow aquifer, which is this blue one right here. You can see the Wasatch aquifers and the Upper Fort Union aquifers. Those are the ones that they're contaminating right there by doing the uranium mining. Side note, if you didn't see it on the map, go back, see that little tiny dot right in there? That's Salt Lake City. It's basically right above that is what they're talking about. All right, advantages of nuclear energy. Gonna move myself again a little bit. Okay, so there's no emissions. That's the big advantage of nuclear energy. All right, there's no emissions, but the mining obviously has a bad part to it. Okay, there's no emissions, it's just steam. Remember those big cooling towers, you're only producing steam, you're not producing nuclear pollution or anything like that. It's just steam. Okay, also advantages, large scale energy production. It produces a ton of heat for every gram of uranium there is. So there's a ton of it. Okay, the predictability of it also very, very, very high. Okay, much better than like solar, much better than wind, all that kind of stuff. It's very, very, very predictable. All right, disadvantages, nuclear accidents. That's what everybody's scared of. Having a nuclear accident, having a Chernobyl, having a 3 Mile Island, Fukushima, those kind of things. That's what everybody's scared of. Okay, the radioactive waste disposal, that's the big, big, big disadvantage. Because overall, nuclear energy is a pretty safe thing. But getting rid of the waste, that's where the big problem is. All right, nuclear accident case studies. We got 3 Mile Island in Pennsylvania, happened in 1979. So these bullet points kind of summarize them up in that little blank there. So the cooling water valve, that was closed. So remember, nuclear energy, boiling a bunch of water, so the steam generates the turbine spins the generator makes electricity. Okay, that cooling water or that water needs to be cooled continually. If you turn off the water to go in there to cool it down, then you have a meltdown. It gets too hot. Okay. 200,000 people were evacuated. The infant mortality and cancer rates may have increased afterwards. And I put may there because it's correlation, not causation. Like we haven't been able to tie the two together. That's why it's just may have increased. All right, next one is Chernobyl. Everybody, I'm confident, has heard of this one. Again, summarize the bullet points here. So during a test, they disconnected the cooling system and removed the control rods. Again, just during a test of it, the plant overheated very quickly, led to an explosion and a big fire. That's what really started the problem because then 31 people died at the time, tons more from radioactivity exposure afterwards. The cancer deaths increased a whole bunch, and then the wind blew that radiation onto the crops, and it also spoiled the milk because basically the crops that the cattle are grazing on got contaminated. The cattle grazed it, ingested all that radioactivity, screwed up all the milk as well. Okay, another one, Fukushima in Japan in 2011. So this 9.0 earthquake triggered a 15-meter tsunami. Remember, a meter is a little over 3 feet. So we're talking like 50-ish foot tall tsunami. That's a massive wave. Okay, major flooding happened. There's a structural damage and the interruption of the power supply. There was fires and a hydrogen gas explosion, the release of radioactive gases, like a whole bunch of different things happened. These are the big things everybody is scared of. Okay, so kind of real quick, jump back to here. Nuclear accidents, that's what everybody's scared of. That's what everybody associates nuclear energy with, so that's what everybody's scared of. All right. So what this is, oh, hold on, calm down. Okay, basically what this is kind of a video that I'm gonna have you guys fill in. Where is it? The last two blanks of page 26. I think that's all I have you written down. Yeah, oh, last two blanks of 26. I can turn my camera off so you don't have to watch me watching a video with you. That's just awkward. All right, here we go. All right. Straightforward. Wait, calm down. There we go. All right. So pretty straightforward thing. Big tsunami wiped out a whole bunch of things. All right. So flip 27, talking about radioactive waste now. Excuse me. So high level used fuel rods. Okay. This is the nuclear waste, is what we're talking about. All right. So the low level, okay, that's contaminated clothing, that's tools, that's the rags, that's the stuff that was exposed to it, but not for a very long time, but that's still considered radioactive waste. All right. The uranium mine tailings, that's another radioactive waste that we got to deal with. Okay. So used fuel rods, that's the thing to put in that top right hand box. As it says there, after time becomes spent, cannot generate electricity anymore, but they're still radioactive. Okay. Again, this is Homer Simpson, makes me think of this whole thing. All right. So uranium 235 has a half-life of 704 million years. That's why this radioactive waste is going to be around for so long. All right. Now, half-lives, side note, this is from a video game that I don't play, just FYI. All right. So half-life, basically the blank there, the time it takes for half of a sample to radioactively decay. So for example, I've given you a few different chemicals there. So sodium 24, the half-life is 15 hours. Carbon 14, 5,730 hours. Potassium 40, you can see 1.26 billion years. Hell of a lot longer than the uranium 235. All right. So this picture here just kind of shows cosmic radiation and kind of what happens in this, that, and the other. Some pretty straightforward stuff. If you want to pause it and read it, go for it. All right. So half-life can be used to calculate, one, the rate of decay, as well as the radioactivity level at specific points in time. So this is what they do to figure out how to date like fossils and things like that, because the stuff that's in them, like carbon 14, for example, decays at a certain rate. So as much is left over, they can figure out by measuring it how old something is. All right, that little graph there on the right-hand side, just kind of skip it. If I was here, I'd kind of walk us through it, but just skip it for now. Okay, so the little gray box under where it says can be used to calculate 1 and 2, copy this down. Okay, so the final amount is A equals what's called A naught. That's what that kind of like that little zero kind of looks like, A naught. Okay, that's the initial amount times half. This is the split factor. After a half-life, 1 pound becomes half-life, for example. Okay, the time that's extended versus the half-life. So for example, I'll go back real quick. Okay, the carbon 14's 5730 years. That's its half-life. So that would go on the H. Okay, half-life right there. The time figured out, you figured it out. So half-life math, we got to figure out some stuff. So units you might see in decay problems, okay, are those the Curies? The Curies is the more popular of the two, just FYI. All right, so this is your units, your example problems. With a radioactivity level of 100 Curies and a half-life of 50 years, what will the radioactivity level be in 200 years? So in 50 years, half the original. So you start with 100. After 50 years, you have half of it. That's the whole point of a half-life. So you go from 100 to 50. Okay. Another 50 years, you'd be at a quarter of it. Okay. So you'd be at 25 Curies. Another 50, you'd be at 12.5. And another 50, you'd be at 6.25. So basically 50 years, 100 years, 150 years, 200 years. You'd be at 6.25. Because basically you're starting at 100. After half-life is cut in half again, and so on and so on. All right. So I'm going to skip over the next two problems. I'll kind of just put them up here. Okay. Just to kind of get through it. All right. So now I think we're on now. Now we're getting to page 28. Okay. So where do we put the fuel rods? All right. So they're dangerous. Kind of my camera's in the way, or me, I'm in the way. I'll put it that way. Okay. So where do we put them? Okay. These things are dangerous for 10 or more half-lives. But remember, it has a half-life of over 700 million years. So we're talking about 700 million times 10 or more half-lives. So we're talking about at least 7 billion years they're bad. That's a long time. Okay, so typically they're actually stored in plants in big, gigantic pools of water, big, enormous pools of water that are really, 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 really deep because the water shields the radiation. For example, They had this thing called the Forbidden Swimming Pool. Okay, there's actually a comic that an artist made one time, and literally it was a safety thing to show that basically you could get sort of close, not very close, or you'd be dead in a couple minutes, kind of close. This used to, no joke, at old nuclear power plants, they would swim in these. Kind of you get done with a long day, take a quick dip, and then you'd be good. Okay. The issue with this, though, is they kind of run out of swimming pools in this area because they're doing this stuff more often. More and more nuclear sites are being developed. They're developing a lot of nuclear waste. So now where do you go? Okay. Now they're going in lead lined dry containers on land. Like in the video, the Fukushima video, they kind of zoomed out all those little, like, kind of bluish things. All of those are lead lined dry containers. All right. So where are we at? Permanent radioactive waste disposal. Okay. Can we do incineration? Can we destroy with chemicals? Can we shoot them into space, dump or bury in the ocean? Like, what do we do? Okay. Most options would allow too much potential for a large amount of radioactivity to enter the ocean or the atmosphere. So, for example, we should shoot it into space. What happens if the rocket explodes at 50,000 feet? Like, the amount of radioactivity spread over a huge amount of area, would be really, really, really in trouble. All right. So one of the things they did was create this place, or kind of designate a place called Yucca Mountain in 1978. Okay, you can see where Las Vegas is. You can see where Reno is, just about an hour and a half to 2 hours outside of Las Vegas. Okay, I've actually been to that site. Basically buried it way, 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 way underground. All right, 30 years of controversy led to the cancellation of the project. Even though it sounds great, they just now have a big kind of hole in the bottom of a mountain that now the state of Nevada has to take care of. Is basically the idea. Because basically, Nevada was just fighting, I don't want this crap in my backyard. And they fought it for so long, eventually they won. All right. Obama ended the federal funding. So now U.S. operating commercial nuclear power reactors. You can see there's a whole bunch of them kind of on the East Coast, more on the West Coast, is what's going on there. All right. So future nuclear power, there's a recent upsurge in applications. Mainly, I think I said this in class today, is basically because of that Russian-Ukraine war. A lot of Europe is reliant on Russia for fuel. So there's a big push in Europe now to become energy independent. So we should do some nuclear power. That's kind of the big push. That's what they're doing these days. Okay. Currently, there's up to 5 new power plants being created in the U.S. in the next decade alone. All right. So here we go. Real quick video again. I'm going to turn my camera off because I don't think me watching a video is very interesting.
Michelle Pilot, please come to the main office. Michelle Pilot, to the main office, please.
Wait, why didn't that play? All right. One more video to see, then we're done with 6.5. Obviously, I had to show that last one because The Simpsons made everything with nuclear energy. All right. That's 6.6. We'll have another video, or I'll have another video for 6.7 in just a couple minutes. Have a good day, guys.